Hey all developers! The topic of today is something that I'm very passionate about, which is test-driven development. But before I start to talk about the topic of this episode, I want to share what I see being out in the field working. What I often see is that during both the initial development and the deployment of a machine, very little care is taken to define automated tests for code that is running on the machines. I often see changes being done to the live system without any tests being defined. Often if a change is done to a running machine, code is not tested at all before deploying it to the machine, but is tested on the live system. Even though these machines sometimes cost several million euros, code is deployed on it without any tests and just, it's just with the spirit of like, just let's see if it works. So coming from a traditional software development background, this is very strange to me as writing tests for code is a common practice there. In industrial automation, doing automated testing is not something you see being done very often, barely at all, even though the machines that our software controls is often very expensive and is used to control an expensive process as well. The automation industry has a lot to benefit by applying test-driven development, and it's one of my goals to make more automation engineers adopt TDD. In this episode, we will look into how we can apply the TDD approach, which will vastly increase the quality of your code and bring many other benefits to your software. Let's start with some theory. So what is test-driven development? What does it mean? It's actually possible to describe test-driven development with one single sentence. TDD is the practice of writing tests before writing the implementation code. I know you probably look something like this, and you're probably thinking, but why? Wait, I know that this concept might sound absurd. You're probably thinking, why would I want to write tests before I write the source code? Why wouldn't I just write the code immediately and skip the tests? Or why couldn't I just write some tests after I've written the code? I fully understand this reaction. I reacted the same way when I heard of TDD the first time. So just bear with me and I'll continue explaining the concepts of TDD, and then I will explain why you should consider using TDD in your software development process. TDD starts with you writing failing tests for the behavior of your code. The tests will be failing as you have not written the implementing code yet. Focus at this point should only be on the behavior of your code. As you only focus on the behavior of the code, you just need the blueprint of the function or function block that describes what the function or function block should do, and write the tests against that. In this phase, you think of what you want to develop. Only once you have written the failing test should you continue to the next step, which is to write code until the tests pass. At this step, it's not necessary that the code is pretty. Only focus on making sure that the tests pass and not any further. In this phase, you think of how you want to develop the code so that the tests pass. Once this step is done, you can go to the last and final step, which is to refactor the code. In this phase, you as a developer can change the names of your variables, change your algorithms, and any implementation details as you find necessary. In this phase, you think of how you can improve your code. Then you repeat this cycle for any additional functionality that you want to add to your code. This cycle is the TDD software development process. So why would we do TDD? What are the advantages with it? When doing software development, what actually happens when the code base grows is that it gets harder and harder to change the code base as the developer gets scared that some existing functionality might get broken. One of the benefits of writing tests is that you will have a regression test suite of your code. If you find it necessary to do any changes to the software, for instance by refactoring it or if you want to add functionality, you can at any point in time easily rerun your tests and see that you haven't broken any functionality. This increases the programmer's confidence in making larger architectural changes when adding new functionality. Once you've written tests for some time, it gets natural to test small sets of functionalities at a time, and thus your function blocks usually end up quite small. TDD thus leads to more modularized, extensible and flexible code. The value of TDD isn't only in the tests themselves, it's also in the value that it drives in writing cleaner code, why TDD is sometimes also called test-driven design. When defining the tests, you'll automatically define what the function blocks under tests should provide, and thus you'll end up with clear defined interfaces for the function blocks. The unit test shouldn't just be software for validating the application, but is equally much a mental engine for the design of the software. As you're writing the test cases, you get better test code coverage and thus fewer bugs. As your test cases are written, you come up with scenarios and run your code that you normally wouldn't run under normal test circumstances, and you can test various edge cases. Any developer that is going to look at your code will get documentation of what the code is supposed to do, just by looking at the test cases. The test cases dictate what outputs every function block should provide given a set of inputs. With this information, any developer that looks at the test cases gets a better understanding of what the code is supposed to do, so the test cases become examples of what the code should do. When developing a certain set of functionalities, you need to define what the functionality is supposed to provide. With test cases, this is exactly what we are doing. Thus, the tests become the acceptance criteria. Because you are writing the tests before writing the implementation, you have to think of what functionality is to be provided by your code. For this reason, you will have to think what interfaces that functionality needs to provide. As the test cases are written first, only these interfaces need to be initially defined. All the other methods and inner workings of the implementing code can be made private. This will result in tidier code. TDD is about the behavior of the code. The value of the tests is that they are the specifications of how the code should behave. So the code is free to change all you want, as long as it can still be validated against the tests. You can improve performance, refactor for readability and supportability, etc. The tests ensure that the behavior remains unchanged. So where do we start if you want to do TDD with Twincat? When writing tests, it's beneficial to use something called an unit testing framework. So what is unit testing? Unit testing is a type of software testing where individual units or components of a software are tested, with the purpose being to validate that each unit of the software code performs as expected. To help you with this, it's beneficial to use a framework for this. Most programming languages in the traditional software industry have unit testing frameworks, and Twincat is no different. For Twincat, there is an open source framework called TCUnit available. TCUnit is an open source unit testing framework that is being used by many companies and organizations across all types of industries. The framework is easy to use. All that is needed is to download and install a library and provide a reference to the TCUnit library in your project. The library and all the source code is licensed according to the MIT license, which is one of the most relaxed software license terms. The software is completely free and you can use the software in any way you want, be it private or for commercial use. The documentation for the TCUnit framework is available at the tcunit.org website, and the source code is available on GitHub. You can always go to these websites to get detailed documentation and plenty of examples of how to use TCUnit. In the practical part of this tutorial, we will go through how you download and install the TCUnit framework on your computer. TCUnit is what is called an XUnit type of framework, and as such has certain components with their respective responsibility. Let's go through them. First, we have the test suites. A test suite is a collection of tests related to each other. Each test suite is defined as a function block and inherits its properties and functionality from TCUnit. Each test suite can have one or more tests, and the tests are the ones that test the functions or function blocks that you want to write. With TCUnit, you execute the tests with something that is called a test runner. the test runner will collect all the test results and present them to you in various formats. Let's dive a little deeper into the details and concepts of TC-Unit. To write tests, we first have to create our test suite. This will be the collection of tests related to each other. Next, we have our function or function block under test, which our test suite will have tests for. You can define as many test cases inside a test suite as you want. Inside your tests, you do something called an assertion. An assertion is a method that verifies some state of the unit under test. If you, for instance, want to verify that a Boolean output of a function block is according to a certain state, you can assert that the output is true. There are many various assert methods in TC-Unit, depending on the data type that holds the state. In order for your tests to be executed, TC-Unit will execute them. But TC-Unit needs to have knowledge about your test suites. In order for TC-Unit to know which test suites exist, each test suite needs to be declared in the declaration of the program that will execute the tests. You can have as many test suites as you want, and each test suite can have as many tests as you want. If you create another test suite, you have to remember to declare it in the declaration part of the testing program. You can also freely choose how you want to organize your tests and test suites. You can execute your tests locally in the development environment of Twinkle 3. When doing so, you will get the results in the error list of Visual Studio or TCXE shell. Let's go through the different components through an example of a test execution. First, we have the statistics. Here we can see the number of test suites we defined, the total number of tests defined across all the test suites, and how many of them were successful and how many of them have failed. In this example, we can see that we have one test suite, two tests which of one is successful and the other one has failed. For the tests that have failed, we get more information. First, we find which test suite function block instance that holds the failed test. Next, we get the name of the test that has failed. Then we get information about what the expected value of our assertion should be and what the actual value was. Here we can clearly see that we expected the test 2 plus 2 equals 4 to output 4, but instead we got 0, which is clearly wrong. We can optionally add a message to the assertion. Before getting to the practical part, I just briefly want to mention that TDD can be incorporated into a bigger umbrella practice called continuous integration, commonly abbreviated CI. In software engineering, continuous integration is the practice of merging all developers' working copies to a shared mainline several times a day. As you can see, writing and running unit tests is part of the CI pipeline. The ambition here is to have tests being executed automatically, for instance, every time someone does a change of the code and commits it to version control. Continuous integration is a topic I'd love to talk more about. Unfortunately, it's a big topic and I won't be talking more about continuous integration in this course, though I just thought that it would be important for you to know about it. Now I think it's time for some practice. Hello everyone, so now it's time for a little bit of live programming again. And we're gonna continue with the program that we've already written. We wrote a CSV persistent event storage in part 5, 6, and 7, I think it was, where we took an event and wrote it to a persistent file. So in this case, just a CSV file, or a file with CSV formatting. There was a tiny bug in this program, I should mention, which meant that only every second event was written down to the file. Luckily, a viewer of this course has found this error and suggested a correction, and the correction is what you have here. So you just copy all of this stuff and then you're gonna have a fully working CSV persistent event storage function. What we're gonna do in this part of the tutorial is that we're gonna extend this functionality with something called a buffer. So there was a limitation in this program, and the limitation was here. If you have an event and you add, so if you just write one event, everything is fine, because then this event is gonna wait for the event, it's gonna open the file, and it's gonna write it down. So this is all fine as long as you only have one event created between every write, which is usually not the case. Usually what you want to have is that you want to have a support so that you can write multiple events at the same time. And I mean, this limitation can be seen here simply by, if we add more than one event to, at the same time. So here we're basically adding the same event 5 times. If we run this program, so let's just open the C drive, nothing here. And this is, by the way, this is gonna create a file on the C drive, events.log, as you remember from part 5, 6, and 7. And so this program has executed. Actually we need to set this to true. We set this to true, and this should write 5 events. That's what you would expect, but it doesn't. It only writes 1. There's only 1 event. So that's a big limitation, and this is the limitation we're gonna fix. We're gonna fix it by adding a buffer so that our program writes this to an intermediate buffer in the memory, and then the CSV persistent event storage is gonna go through the buffer one by one and write them to disk. And we're gonna do this using test-driven development. What we're gonna do first is that we are gonna take the functionality that we have, parts of it, and move it to a library. The reason that I want to move everything to a library is because we have to have somewhere where we're gonna run our unit tests. This is the main executable program, right? Just imagine that this is the program that's actually running in the machine. That's the core business logic that we want to have running in the machine. For the unit tests, we want to have a separate program for that. We need a separate program for that because we're gonna write our tests and we're gonna have our function blocks and everything, and then we're gonna need to execute those tests somewhere. And this execution of tests shouldn't be this program. It should be a separate program that only has the responsibility of running the tests. So we're gonna start with just creating a library project, and I'm gonna call it, what can we call it? Naming is always so hard. So we can call it event buffer library or something. That's just as good as any name. And then we're gonna create a new PLC project. We can just leave it as untitled. And we will rename the main program to program test. We can leave it as main, but for tests, I generally rename the execution program to PRG test. This is just my standard. You can use whatever standard you want. Next, we're gonna copy the function blocks that are related to this functionality of event storage, event buffering, and event writing to this library. So I'm simply gonna move this stuff over to the library. So we're gonna need the event logger. Yeah, we can actually copy everything except the main program. So we just put everything in the library. Like this. We can copy the DOTs as well. I didn't remove them from here actually, so I'll just remove them from here. Now this doesn't compile obviously because it doesn't have all the POUs it needs, but that's gonna be solved because we're gonna soon integrate this library into this program. One of the changes we're gonna have to do is to the CSV persistent event storage, because this guy only manages one event at a time. I mean, if you look here at the store event call that we created, the store event method that we created, you know, when an event is added to the store event, it's stored here, and that's just one event. We don't have anything. So we're gonna have to make some changes here eventually, but we're not gonna start with that. We're gonna start with creating the buffer itself, the buffer to hold the events. So for this, we will create a function block. And this is test-driven development, right? So what we're gonna do first is just create what type of functionality do we expect from this buffer? How is the interface? How do we communicate with this buffer? We don't write any implementation code. We're first going to write this simple thing that just describes what this function block should do, what we can do with it. Then we're going to write the test that describe the behavior of this function block. And then we're going to write the actual implementation code, but only after writing the test. So it's very important that we write the test first, because it's going to force us to design the software in a very modular and robust way, which is one of the key points of test-driven development. That's why I sometimes say, or what you often read, is that you can call it test-driven development, but it's equally important to call it test-driven design. So we're going to call it CSV event. No, actually it's not CSV. It has nothing to do with CSV. It's just an event buffer. That's what it is. And what do we want from an event buffer? We want to be able to store events, right? So we want to add an event, and it should store the event. And maybe we want to get something back. Maybe we want to know whether there's an error, just to indicate, just okay. Yeah, just an error to indicate whether the add event was successful or not. What do we want to do more? We want to get an event, so we want to be able to get an event, and when we do that, we want the buffer not just to get it for us, but also to remove it. Right, because once we get it, there's no need for it to be in the buffer. I mean, you could think that you could maybe want to have two separate methods, where one is getting it and deleting it, and one is just getting it without deleting it. But we're just going to write the one that's get it and deletes it. So get and remove event. Okay, and this one is providing us an output, an SD event, but it's also, we should also get an indication whether it was successful. If the buffer is empty, it shouldn't be successful, for example. So be error, bool. And I mean, that's basically what we need. We might also want to know how many, there's one more thing that we might need, and that is how many events are in the buffer. It's not super important now, but if you come to think about it, when this persistent event storage is going to go look through the buffers, it needs to know, is there anything left that I need to write to the disk? So we can just get number of events, return just on this, no inputs. So, I mean, if there's 0, it's going to return 0, obviously. And that's it. As you notice, we haven't written a single line of code for the implementation part. Nothing here, nothing here, nothing here. And that's the way it should be. Now we're going to start to look into writing tests. Before we do that, we have to download the TCUnit unit testing framework. And you do that by going to github.com/tcunit. And you click on this pinned project here, TCUnit. You go to releases, and you go with the latest one. So when you watch this video, there might be a newer version, but right now TCUnit 1.2 is the latest version. And then you download tcunit.library. That's going to download the file. Then we're going to install it. So then we go to Twincat, PLC, library repository, install, downloads, tcunit.library, open. That's gonna install, that's gonna install the library here. So now we have the library downloaded, and that's everything you need to do to have access to the full unit testing functionality of TCUnit. Next, we need to add a reference to TCUnit, like this. And now we can start to write unit tests. The first thing is that what I usually do is I create a separate folder for all my tests. And so we have our POUs, that's our usual business logic. That's where we have all our usual stuff. And we will create another folder where we add our tests. We can actually move our program tests to test. So that doesn't do anything right now. It's completely empty, which is the way it's supposed to be so far. The first thing is that we're gonna create a test suite. So a test suite is a collection of tests. We need to create one, and we need so that TC-Unit can execute those tests. And that's just a simple function block. So we create a function block for that, and we're gonna write tests for this event buffer. So I will just call this event buffer test. Doesn't have to be this name. You can have your own naming standard. This is just what I follow. To make this into a test suite, it has to extend the FB test suite function block, which is a function block that is part of TC-Unit. So this does some magical stuff here in the background. Not super important to know what it does, but this is what you have to do. I actually forgot to mention one important thing here is I just talked about the library itself. I should mention that, I mean, this course is gonna cover the most important thing of what you need to know about writing tests in TC-Unit, but you always have the website. So you can always go to tcunit.org, and here there's a full manual with the unit testing concepts, a very basic introduction guide to writing tests, and then a super big course, more or less, that shows a real world example, you know, with IOs and everything and hardware, and yeah. This is really good if you really want to dive deep into unit testing. And of course, lots of other stuff. So an FAQ, if you have, you know, the most common questions for TC-Unit, and yeah, lots of goody stuff here that you can go to after you watched this part of this course. Okay. So the first thing is that we have to think about what do we want our tests to do. One thing is naturally that we probably wanna add some events to the buffer and then read those back and see that we get those same events back. So we can create a method. The method is gonna be what executes the test, right? So we will have one method for every test. So remember, the test suite, this guy, that's the one that collects the tests together. So this is gonna execute all the tests, but we need to add those tests now. And I'm gonna start with adding a test that, yeah, and here, this is just your imagination that sets the limits. But remember that generally your function blocks and your code is only gonna be as good as your tests are. But so, what can we do here? Add 3 events. Yeah, I'm really bad with coming up with good names. Expect all to be correct and successful. So this is just, if we add 3 events, this is what we're gonna do, and this is what we expect to happen when we execute the test. We expect everyone to be correct, so the data we put in, we expect to get it back, and yeah, the whole read should just be successful. And this can just be a private method because it's just going to be executed in the test suite. And here we can add all our test objects that we're going to do. So in this case, it's going to be our event buffer. The first thing you do is that you write test and then the name of the test. So it's just a string. I usually just put the name of the method, but it doesn't have to be that. And then test finished. So everything in here between defines the test. Okay, the first thing we need is the event buffer itself. That's what we're gonna test. So the subject under test. And then we need some data to fill it with. So we can do a couple of events, 3 different ones. And each event was an SD event. So we need to create a couple of events. So event type 1, and that could be, well, actually, let's create them as structures. So st event 1, that's an SD event. and it's gonna be an event type of alarm. This guy is gonna be, yeah, this doesn't matter. Just put some numbers as long as you get the same stuff back when you read the event. Event identity 42, it's a classical one. Comma. Event text, hi there. Wait, we have something. Ah, yeah, okay, so why? Oh, wait, why doesn't this work? Ah, a comma. I missed a comma. Date and time. Let's just take one of the date and time constants from internet. Date and time. Okay, then we just copy this guy and make 3 in total. So SD event 2, that can be slightly different. And a third event. So these are the 3 events that we will put into the buffer and expect them back. Okay, 3 events. Now we will add the first event. And we get an output error. So we will store that somewhere. The error. And now we will do our first assertion. So the assertion is, yeah, the word basically says everything. It just checks that is the value that we got what we expected, right? So we don't expect an error. And this we can do by various different assert methods. So there's, if you do assert, there's assert methods in TCUnit for basically any data type that you can think of. There's for booleans, I mean for all the primitives in TwinCat. So we use the one for bool to check whether error is false. But there's also a short version that's called assert false. That just does what it says. It asserts that we don't have an error. And I just actually realized that error is not the best thing to do, because normally every variable is instantiated with false, which means that this error will of course not be true in this case. I mean, if you come to think about it, we don't have any code here for the event buffer, right? There's nothing here, which means that error will be false. And that's a bad thing for us, because then it means our test is gonna be fine without us actually writing any code. So we should do it the other way around. We should actually return whether we get an OK or not. And for this guy as well. And this is, again, just shows what I like with test-driven development. It just forces us to think into these cases where, you know, we will have tests that will fail. So when we run the code without an implementation code, which means that the only way they will not fail is if we write the implementation code, if it makes any sense, which is really good. So be OK, we store that instead. And then we have to assert true instead. We have to make sure that the condition is true. And here the condition is be OK, so this guy. So we assert that what we get out, what we get back is OK. That's what we assert. And we can add an optional message. So add event 1 was not OK, for example. Then what can we check more? We can check if we have one event, because we have get number of events. So we can assert equals, the events was on udint, assert equals udint. Wait, before we do that, we have to get the events, the number of events, and we do that by event buffer, get number of events. We just store that somewhere, and number of events. We assert that expected value is 1, because we only added 1 event so far. The actual value, the one that we are asserting against, is number of events. That's what we got. Message not correct, or expected 1 event. Yeah, then we can pretty much do the same thing for the other 2 events. So this is kind of like, you know, event 1. Then we just copy this guy. We add a second event to the buffer, but this time it's going to be the event 2. We expect the addition to be okay. So we assert true okay, because we store it in okay, be okay here. Add event 2 was not okay if it fails. Then number of events should now not be 1, but 2, because we have added 2 events. We haven't read any events, so both of them should be there. Expected 2 events. And then we do the same thing with the third guy. I don't know if you notice it, but this really forces you to think about the software. I mean, I already realized one problem with the software, and that is that we haven't defined anywhere what the maximum number of events should be. You know, we could do it in 2 ways. We could either put the limitation directly hard-coded into the function block itself, you know, the event buffer. We could say that an event buffer should always only manage 10 events, or 12, or 3, or whatever. But I don't like that. I think we should be much more flexible than that. I think we should be able to provide from the outside how many events this buffer should handle. So yeah, that's something we will have to get back to quite soon, I think. And this is what I like with test-driven development. It makes my brain just think about all this. It makes me think about the design of the software, and that's what I love about it. Anyway, add event 3 was not okay. Number of events, we should get it. Now we expect 3. Expected 3 events. Okay, so now our test says that we are expecting 3 events, and that we are expecting them to be successfully added. Okay, but that's not enough for the test. Now we should read all of those events one by one and make sure that they have the data that we expect them. So this information is what we should get back. And I forgot to mention it, but this buffer is a first in, first out buffer. It means that if we add an event, then that event should be the first one that goes out when we read it as well. So if we add these 3 events, it means that once we read them, the first one is going to be the one that we're going to read the first time. And then it's going to be the second one and the third time. So in that order, which means we're going to read the oldest one first, which makes sense in our case, because, you know, if you write this to a file, we want to make sure that they're written in the order that we added them. Okay, so it's actually an event FIFO buffer, you could call it. That would probably be a much better name. So that's what we're gonna do. We're gonna read these events. We're gonna do it by going to our event buffer, get and remove event, as the event. We're gonna have to store the event that we get from the buffer somewhere. So just do it here. And yeah, BOK. We can store that into BOK as well. So first of all, we should make sure that we could read the event successfully. And then we again do an assert true. We check that the read was successful. So read of event 1 was not successful. We could also do, one thing we could actually do is to assert that we have 2 events now, right? Because if you read one, because we didn't just get it, we also removed it. So yeah, that actually, let's do that. So now we should have, let me just put some title here so it's easier to follow. And I should do the same here. Add event 1, add event 2. These comments are not necessary because you can obviously see it from the code, but yeah. Read event. So hopefully event 1 or the first event. Now we're gonna assert that we only have 2 events there. And let's try this instead of just, I don't know if this is possible in structured text, instead of using an intermediate variable, let's just call the event buffer directly. Okay, that worked. Yeah, that's neat. Expected 2 events. But now we have to check all this data. So we have to check whether the data here is what we expected it to be. And so we need to check each and one of them. And all of them are stored in this event. So let's start with the first guy, event type. And event type, this is an integer. So all enumerations, if they're not explicitly specified, are integers. So we can simply check assert equals int expected. I expected an alarm. Actual, I got st event, so we stored it here, right? And event type message. We can skip the message here. It's gonna, we can just I changed my mind. Expected event type alarm. The next one is the event severity, and this is also an integer. Copy this guy, but now we expect this, but the actual was stEvent.eEvent severity. Expected event severity critical. Writing tests is really fun. Well, depends on your definition of fun, but I think it's fun. It's fun because I can feel the quality of the code. It's just... then we need to read the event identity. That's an udint. We expect it to be 42. And the actual is stEvent and event identity, right? Because again, when we read the event, we got it into stEvent. And that's where we have all our data. That's where all our data should be. Message expected event 42 something. Next one is the event text, so that's a string. Expected header. Actual event text. Message expected, yeah, so here we can let's just skip this. You get the point. This message is gonna show up if the test fails. So it's gonna help you to know why the test failed, or which test failed, which assertion failed. The next one is date and time. That's what we're gonna sort this guy, and we expect it to be this. But the actual is this. And the message is, I'll just leave it empty. And I think that's basically everything for event 1. And then it's just the same for all the other events. So what I'm gonna do is that I'm just gonna copy this and do the same assertions and the same tests for the 2 other events. So I'll just... Okay, so this is event. So I copied this down here. Read event 2 was not successful. Now we don't expect 2, but we only expect 1 to be left. So there was 3 originally. We read 2 of them, read and removed 2 of them, so there should just be 1 left. So expected 1 event. Now we expect it to be a message. I'll just remove the text here. I expect it to be an error, and I expect it to be a 43, and I expect it to be height there too. My fantasy is not very good, and with a slightly different date. Yeah, sorry, this is actually too big, so I have to make this slightly smaller. Yeah, because what I copied was the maximum constant for the date and time from the Beckhoff website. Okay, and then we read, get and remove the last event. So read event 3. Now, so I just, maybe this went a little fast. I copied the event 2 and put it down here, because now we're gonna read the last event that should be in the buffer. We expect now when we check how many number of events, it should be none, right? Because we read all 3 of them. Expected no event. No event left. And the last one is gonna be an alarm, and it's gonna be a verbose event, and it's gonna be 44, and it's gonna be height there 3. And yeah, I'll copy this guy for the date that we expect. And that's basically our test. So our test says, I want to add 3 events. And when I add them, all of them should be successfully added. Then I want to read each and one of them and make sure that the data I get is the correct data that I added in the first place and that they come in the right order. That's basically what our test does. To execute this test, we have to add it into the body of the test suite. So we go to the test suite and we execute this method. So now we have our full first test defined. And the next thing we have to do is we're going to have to add more tests. I don't think this test is enough. I think we should have more tests. But before we add more tests, we have to instantiate this test suite in the program tests. That's all you do. You instantiate it. And this gives a handle to the TC-Unit framework to the test suite. So all the test suites that are instantiated here are going to be executed. Then you have to tell the program test to execute the TC-Unit test runner. And this you do simply by writing tcunit.run. So what this does is that this is going to execute the home framework. And because we declared these tests here in the declaration part of the program test, then TC-Unit will have a handle to them. But you don't need to explicitly execute the test suite like this or anything. That's not necessary, because the only thing you needed to do is to extend the FB test suite. That's now TC-Unit has everything it needs to execute it. So we could actually already now execute this test and just see that it fails, because that's what we want. We want it to fail. And then we're going to add some more tests just to describe the behavior of our program. So let's run it. Of course, I have to do the core isolation because I'm running this on a virtual machine. Restart, yes. Yeah. Then usually this comes a little out of order. Just press description once and then it's all going to come in order. And here you see now failed test, PRG test, FB event buffer test. So it's this guy, this test suite. And then we have the name of the test that has failed. So add 3 events, expect all to be correct and successful. You know, so it's this test obviously. And then all the failed assertions. So we already have the first failed assertion is we expected true, we got false. Add event 1 was not okay. It's this first assertion, right? Because it can't be okay because we haven't written the code for it yet. And then, you know, all these assertions we do, every single one of them is gonna create one line here that describes the failure of the assertion, because all these assertions are going to fail because we haven't written the code yet. So we have lots of failed assertions, and at the bottom you have the test suites. How many test suites, how many tests, and how many were successful, and how many are failed. So we have one test suite. It's only this guy. This is the only test suite we have. We only have one test. It's this guy. And we have 0 successful tests, obviously. And 1 failed. So that's a good start. Having failed tests is something very good. That shows that your tests are good and that you have something to work against, so to make your tests not fail. Before we continue writing tests, I want to fix one thing here. So we realized together that there is a limitation with the event buffer. We don't have any specification of how many events the event buffer should handle. And I think we should put this outside of the function block. So the maximum number of events should be, the storage for the event should be outside of the function block and provided as an input to the function block, so that the function block internally knows how many events it should manage. And the way I thought is that we'll simply create a constructor for it that defines where the buffer is and the size of the buffer. So we do this by fbinit that we've already walked through, and we need an array buffer to store it in. So we need to provide a pointer to array buffer, pointer to byte. It's going to be a byte array, and we need size of array buffer. That can just be an udint. And then we need to store this internally in our function block, so that the function block internally has this information. So I'm gonna copy these guys. I'm gonna create them internally. And then we need to store this pointer to array buffer is this one. And this size, oops, what happened there? Is this one. So, which means that our event buffer will have a handle to the array buffer, so the byte buffer, and it will also know the size of the whole buffer, which we need to know. Otherwise, I mean, we could just simply say that we create an internal memory ring buffer or a FIFO buffer in here with a fixed size, but that's a little boring, because then the user of this event buffer is locked to a specific size. You know, if he wants to have, if we say that it's only handle 3 events, then, you know, what if I want to have 10 events in my buffer at the same time? What if my system should be able to handle lots and lots of events at the same time? So it's better to put it outside. And again, you see a little bit maybe where these tests, they force us to think into terms like this, which is of course very good to make a robust and good design. Now, to use this, we need to provide the event buffer into this. So if I try to compile this now, it's going to complain. So let me just remove this, rebuild, because it's going to say no match in fbinit method. Yeah, exactly, because the fbinit here, these two guys are not provided. So we need to provide them to the constructor. And we need to create these buffers in our tests. So we have to define what should the buffer be. What is the size of our buffer? It's completely flexible now. We can set it to whatever size we want in these tests. For simplicity, we should set it to size 3, for example, because we only need 3 for this. So let's create an array buffer. That's an array of... I always forget the syntax for arrays. After all these years, I still forget syntax. You know, it's just proves that, you know, you always go to Google or Stack Overflow for stuff, because, you know, there's just too much stuff to keep in the brain. A certain size, and so here's the question now. But how do I define the size? If I want to store 3 events, how do I define this in here? Is there a smart and easy way to define that I maximum wanna handle 3 events? And yes, there is. What you can use is that you can say 0 to this total size of one event times the number of events that you want to handle. So size of SD event times 3, for example. That's the array buffer. What this says, we created an array buffer of bytes, an array of bytes where the size is 0 to 3 times size of SD event. So that gives us enough bytes to handle 3 events. And now we need to provide the pointer to this guy for our event buffer, because that's where the data is going to be stored. And that's done by address to the array buffer. And the size of the array buffer is used using the size of, like this. So now we moved that outside of the event buffer. Now, if you want it to be something else than 3, now we handle 10, for example. Super convenient. So we have that out of the way. Now we will continue writing tests. The next test is related to what we just did. So let's test the case that we add more events than there is space for in the buffer. That's a good test, right? We want to make sure that if we add too much, we should get some notification of it, because then we can create a message to the operator or something that says, hey, there's a limitation in the system. We can't store enough data in the buffer. So let's just create another test. I will call it let's say we have an event buffer of 3, but we want to add 4 events. Then obviously the last event should not work. So add 4 events, expect all to be added except the last one, maybe. These names are quite nice. It's good to use some descriptive names, because the name itself describes what you do and the expected behavior. Private. Then I'm gonna copy the buffer stuff from here, and I'm gonna copy the event as well, so we don't, we can reuse the test fixture stuff. So we have 3, the size of 3, and now we are gonna start the test with this keyword test. The name is gonna be the same name as the method. It doesn't have to be. This is just my recommendation. And then test finished, and everything in between here is our test. So what do we want to do? We want to add some events. To do that, we need our event buffer. Add event. SD event is SD event 1. I'm just going to add the same event over and over again here 4 times. And BOK is going to be, we can create a variable, BOK return. And here we can do our assertion. Assert true. This should have worked, right? Because what we want to test here is that we add 4. The first 3 should work. The last one should fail. So condition is BOK return. This is what should be true. The message is should have been added successfully. And then we do the same thing 3 more times. I just want to be clear here. So this is event 1. This is event 1 again. Or actually, I just write event 2. I mean, reusing the same event, but it's still another event that's added. Should have been added successfully. Then event 3. This should also have been added successfully. But now, because we only have space for 3, event 4 should the OK return should be false, so it should not be OK. So it should not have been added successfully. So we do an assert false instead of assert true. So we're basically just testing that the limits are okay, that our buffer can handle 3 events but not more. And then we need to go to the test suite and just add this test in the body of the test suite. So now we have 2 tests. We can test this by executing the tests and just see that we have 2 failed tests now. Lots of stuff. 2 tests and 2 failed tests. Great. Yes, you should be happy when you have failed tests. That's a good thing. But you will probably be even more happy when the tests are not failing. What can we test more? Yeah, now I don't have any fantasy. Yeah, let's go in the other direction. What if we add 1 test but read 2? Then the second read should fail, right? If you only add one event but we read 2 events, then the second one should fail because there is only 1 event to read. So let's write another test. Add 1 event, get 2, expect the second one to fail. Expect the second, yeah, to fail. That's private. As usual, write the name of the test first. Test finished. Everything in between is going to be our tests. And we'll also copy the event from the array buffer, and this stuff we can copy from the other tests. So what we want to do here is that we want to add 1 event. Add 1 event just like the test says. So event buffer, add event, as the event is this test event that we're using, and be okay is just, we don't have to assert that the add was okay here because we already have other tests doing that, and that's an important factor writing tests as well, that you don't have to, if you write a test that tests something, you don't have to test the same thing in other tests. That doesn't, that's not necessary. What we want to focus on here is, now we've added 1 test and then we want to get 2. But we expect the first one to be correct, but not the second one. So that's exactly what we're going to do. Now we're going to go back to our event buffer and get and remove event as the event. And we restore this somewhere as the event return. As the event, restore this event, and then be okay is gonna be okay return, and here we expect this return to be okay because we added 1 event and we got it, and that should be fine. So we assert true, that condition is, we assert that be okay return is true. Message expected, what can we say, expected okay to be true. I don't have any fantasy now. Now is the second thing here. Now we will do a second get and remove event. So this is round 1, round 2, but because we get and remove the event from the buffer, there should be no events left in the buffer. So this OK return should return false. So we assert false. Expected OK to be false. And I think that should be enough. Yeah, I mean, we could add more tests. So let me just execute this so we have it executed. So we have these 3 tests. We could add more probably, but I realized that this recording is quite long, so we will just be fine with this. And just take my word for it. Whenever I find a bug in my software, it's usually because I failed to write proper tests for it. So it's always good to have good tests. And I think this is good enough for now. Then let's just run them and see that we get 3 failed tests. Three tests, 0 successful, 3 failed. So now we've done the red part of this red, green, blue picture that you saw in the presentation I made before. So we've written tests that fail. Now we're gonna do the green part, which is making sure these tests pass. So we're gonna write the implementation code for them. In other words, everything that's all these missing methods.